Okay, so right, so this is going to be a talk about some joint work in progress with Teleman, and so I'll try to stick. Well, I hope my slides stick to the convention that G will be a compact connected Lie group, and GC will denote its complexification. So so the setting that I want to thing that I'm trying to generalize goes back to classical work of Kirwan. So let's say you have a compact, or you can have a little bit more generality, but a compact symplectic manifold, and with a Hamiltonian G action, and consider the moment map. And throughout my talk, for simplicity, I'll assume that I've chosen a reduction level so that you can the quotient is again a symplectic manifold. So something Kirwan proved in her thesis is that if you look at the restriction map on equivariant cohomology with rational coefficients from the total space to the reduction level set, which you can then identify with the cohomology of the quotient, that's a surjection. And this theorem, as at least if you modify the statement slightly and say you look at the equivariant cohomology with of the level set, that it remains true independent of whether the action is free or if they're stabilizers. But recently we sort of the one thing this wrong way.
So even positive dimensional stabilizers.
Yeah. Well, it's just if you formulate it as looking at the equivariant cohomology of mu inverse of 0, then yeah. So the idea of her proof, and I mentioned this because it's it'll come up later, is to look at a certain function. So look at the mu squared function, and so the norm squared function. So with respect to some invariant inner product you choose on G, and the norm squared. So it isn't actually quite a Morse function. For example, in the case that we were discussing a second ago, if you had positive dimensional stabilizers, the 0 level set is always a critical set, but it wouldn't be sort of smooth unless it's a regular. The 0 happens to be a regular value. And you can have more complicated singularities at other fixed point sets as well. But nevertheless, she proved that you can basically, this function can basically be treated like a Morse function, and so there's a Kirwan stratification. If you look at the Morse stratification by descending manifolds, this gives you an equivariant stratification of the manifold. And then the main result is that the function mu squared is equivariantly perfect. So in other words, if you have such a stratification, you get a spectral sequence, in this case it collapses. So like the spectrum, so as I was saying, mu inverse of 0 is always there's always sort of a main cell that collapses onto mu inverse of 0, and that's sort of the lowest stratum in your filtration. And so there's always going to be, because this will always be sort of the lowest, the deepest quotient will be the equivariant cohomology of mu inverse of 0, which gets identified with the cohomology of the quotient and the free or finite stabilizer case. Okay. So one thing that, is sort of interesting is, actually, so that's a nice story, but,
The theorem, so the cohomology, rational cohomology, these other strata vanishes, is that?
no, it wouldn't vanish. It will, all of those strata will contribute. So like, for example, let's maybe
Oh,
like,
sorry, it's surjective.
yeah,
Yes.
so like
Yeah, I
just,
got that.
but just, yeah, it's a good, thing to put up in a. Good excuse to put up an example from which you can understand most of the stuff, of P1 acted on by a circle group. So and then you're just looking at, so you have your moment map. You could imagine it's normalized to be something like -1 to 1, and and then the critical locus of mu squared would be the fixed sets, and then also this whatever your 0 level set would be. So it's not the case that you have surjectivity. So this carries odd dimensional cohomology, so it's not the case you have surjectivity before you pass equivariant theory, but after you do, then you have surjectivity. So that's nice. So this is maybe, it's a story in and of itself, which is recently we sort of observed that you could, if you input a little bit of like chromatic homotopy theory, then you can actually prove the surjectivity. So with integral coefficients. So in the case of a free action, so this theorem fails if you have stabilizer groups, but if you if you have finite stabilizers, you can invert all the orders of the stabilizers, but with positive stabilizers, there's no such integral theorem. And so this is sort of not exactly what I want to talk about, but it's crucial. It's going to be important for making all of our results work integrally. So in fact, in the case of a free action, the Kirwan map is surjective integrally. And then it's sort of an interesting question whether it works in any sort of complex oriented homology theory. So that's sort of not, it'll be a different talk, but in either case you have a surjective map, and it's natural to try to, you can imagine that your M is, say, Pn or something very simple, and your quotient is something you're actually interested in. And you're trying to describe the cohomology of the quotient. And in that case, you'd like what you'd ideally want is to say, or in fact, you could imagine that you have a vector space. Even that would be an even simpler case. It's not compact, but it's sort of, as long as you have a proper, things are sufficiently proper, everything, Kirwan surjectivity applies in that case as well. So you want to identify generators of the kernel, and that's and ideally you'd like sort of ring generators of the kernel, like you like just a finite number of generators, and that's actually something you can't classically. There are certain descriptions of the kernel, but they tend to be kind of additive presentations, sort of about maybe cut and pasting the equivariant cohomology. You take this stratification and then you try to figure out what pieces maybe correspond to these other additive. They tend to be kind of additive presentations of the kernel, not giving you just like a finite number of generators of the ideal. So what we we'd like to do is the approach we take is actually kind of motivated from 3D gauge theory. So if you have a compact symplectic manifold, this was sort of Constantine's ICM address about 10 years ago now. If you have a compact symplectic manifold with Hamiltonian G action, the idea is that it should define, so I'll say some words and I'll try to explain as much of those words as actually can be made sense of at the moment. So it should define an object in a so-called Rosansky-Witten 2 category of associated to a certain holomorphic symplectic manifold. What exactly that holomorphic symplectic manifold is, I'll describe it very soon. There's a small problem with this story, which is that so Rosansky-Witten theory, it says basically like, if I have a two-dimensional field theory associated, so the B model in 2 dimensions associates the derived category of coherent sheaves as its boundary state, but we don't actually know how to sort of do the 3D version of that at the moment. So we don't actually know how to define this 2 category, but roughly speaking, what we think this 2 category should be is it should have some sort of, maybe algebraic Lagrangian. So I should say, I didn't say this. You can actually sort of, so this is supposed to be this Coulomb branch or BFM space is supposed to be the space of the pure gauge theory. There also, if you have a representation, there's variants that won't play. They're very interesting. They were studied by various people, Braverman, Finkelberg, and Nakajima. They won't play such an important role in my talk. But in general, you have one of these spaces, and what we expect an object of the 2 category to be should be some kind of algebraic Lagrangian submanifold of this holomorphic symplectic manifold, and then it should carry some kind of sheaf of categories over it. And so what this prediction means is that if you have a compact symplectic manifold with Hamiltonian G action, I shouldn't pick in particular be able to produce for you some kind of canonically some algebraic Lagrangian inside of this inside of these Coulomb branch spaces. So I don't as I said, the 2 categorical picture is not yet well defined. The 2 category is not actually well defined, but what I want to do today is explain that if you sort of decategorify everything, I want to explain how you get some nice formula for quantum cohomology of GIT quotients. So, and in particular, you get kind of very concrete statements out of this picture.
Concepts coming to the picture.
How does it come into the picture?
Yeah.
What I'm saying is, if you have a symplectic manifold, then it should define, every symplectic manifold should define for you an object in this 2 category. That's sort of, so this is yeah, that's
there's a G gauge theory and any so anything that with a G action and you think of it as a boundary condition.
Oh,
that's G gauge theory.
yeah. So what is this space? How do this? I promised to explain what this pure Coulomb branch. There's many different names. Pure Coulomb branch, BFM space, But it's a fairly simple thing to think about, so
BFM or BFN?
BFM, okay. Yes, so BFM meaning the, yeah, Braverman, Finkelberg and no. Bezrukhovnikov, Finkelberg and Mirkovich versus Braverman, Finkelberg and Nakajima. So the ones with representations were the BFM contributions. These are let's just say that the pure gauge, the mirror to pure gauge theory, let's say, it's pure Coulomb branch. So here's how we construct it. So it's a fairly straightforward thing. So you have the you take this, you're looking at the base loop space of your group, and you look at it equivariantly with respect to conjugation, and then you equip it with the Pontryagin product. And so you look at this. This is kind of equal. The one small warning is that this kind of equivariant homology is it's not the usual equivariant sort of Borel equivariant homology, but it's maybe like, I don't know, something called like co-Borel homology. So in other words, sort of you're looking at cycles over in the BG direction, which have finite codimension instead of finite dimension, roughly speaking. So there may be different ways to formulate this theory, but it's something you can do in equivariant homology. And what you get is a Hopf algebra over the cohomology of BG. And so in particular, you get this spectrum. If you take its spectrum, you get a group scheme over this cohomology. So you know this map from the this map here to this this was called the Toda integrable system. So in particular, the generic fibers are Lagrangian tori, algebraic Lagrangian tori. It's a completely integrable system. So and then what Bezrukhovnikov, Finkelberg, and Mirkovich proved is that, at least away from, you know, there's finally many bad characteristics, but this spectrum is a smooth holomorphic symplectic manifold. Well, in finite characteristic, I guess you'd say smooth algebraic symplectic variety. And the symplectic structure, where does it come from? That's sort of an interesting thing. Well, this algebra can be kind of, if you take into account this additional S1 symmetry on the loop group, the base loop group, then coming from rotation, then that gives you a quantization of this algebra. And anytime you have a quantization, you get a Poisson structure. And what they proved is that in this case, this Poisson structure that you got is actually symplectic, not degenerate.
This means deformation quantization.
Yeah, exactly. So, you know, additively, this would be just because so this is kind of concentrated in even degree, like additively, this would look like the like this cohomology adjoins a formal variable u, but the product is a non-trivial deformation. It's non-commutative actually. So just to give some example of what this the space might look like. So if you take, so in the case where you, yeah, maybe I could give a general way of thinking about thinking about this holomorphic symplectic manifold. So if I take, at least in, maybe I'll stick to characteristic 0. So if I look at characteristic 0, this sort of a version of the usual Borel theorem about the cohomology of BG, and T here is take some maximal torus, says that this, if I want to just understand the T equivariant homology of omega G, then sorry, the G equivariant, I can view it as the Weyl invariance of the T equivariant homology, and for this, there's a map from, I just look at co-characters. So if I just consider this my co-characters into the omega G, and what's interesting about this map is that, you know, if you look at the T fixed points of the T action, the T fixed points of the T action on the, at least, you know, maybe polynomial loop space, then the fixed points are exactly the co-characters. That's something, and so by a T-abot localization, if you tensor with a fraction field, this becomes an isomorphism. And so algebrogeometrically, so this space here, if we take the spectrum of this, this is like a cotangent bundle of the dual torus modulo the Weyl group. And this space can be thought of as a kind of a symplectic affine resolution of singularities of this Weyl quotient. So, and you know, so concretely, what does it do? Like in this case, like how does this come about? In this case, well, in this case, you would have a rank. You'd look at SU2. You'd be looking at a rank 1 group, and so you'd be looking at your cotangent bundle modulo the Weyl group would be given by you'd have 2 variables, H being the variable on the C factor and Z being the variable on the C star factor, and the Z2 action you know, acts in this way, and the Coulomb branch is given by just blowing up the fixed point 0, 1, and then removing the proper transform of the 0 section. And you know, in this case, what you get is the so-called Atiyah-Hitchin manifold. So, it's already something interesting. In general, you know, these are sort of interesting symplectic manifolds, algebraic symplectic manifolds to play with. So, okay, so my strategy for, you know, for what I told you, I tell you something about quantum cohomology. So so let's say, so I'm going to stick to some, you know, the story works best if you stick to certain special symplectic manifolds, which are called monotone symplectic symplectic manifolds. So these are manifolds where the cohomology class in the symplectic form is actually equal to the first Chern class. And that's because, you know, in this case, the quantum cohomology, it actually converges sort of, you know, generally when you do quantum cohomology, there's sort of a formal parameter that measures, you know, all of your quantum cohomology products tend to be series that don't converge. You don't get something, you know, well defined over C. But in this monotone case, or if you're an algebraic geometry person, Fano case, you get just all of your quantum products are sort of polynomial in the area parameter. So so what do I mean? So I'll be looking at S1 cross G equivariant quantum cohomology, and the G action will act on the symplectic manifold, but the S1 action is you know, where does it come from? It's sort of this, if you know, if you're maybe more if you think of quantum cohomology as being Floer cohomology, it corresponds to the loop rotation variable on the free loop space of M. It sort of gets obfuscated in this quantum cohomology picture because it you know, additively you just tack on, you imagine that you know, basically quantum cohomology sort of in the compact case, everything in terms of the loop space, everything sort of gets retracted down to the constant loop. So sort of, you know, you can think that this S1 is just acting trivially on M, but really it's coming from this loop parameter variable. So you add in an additional variable U here, and then you have just one Novikov variable, which measures the you know, which will keep track of the area of your holomorphic spheres that you're going to be counting. And so, you know, if you just forget about U, so you forget about this U variable, what you have is just the quantum product. So you know, what you want to think is that you're counting sort of, you know, spheres with 3 mark points, and you know, maybe 2 of the mark points pass through some kind of cycles, and then you want to sort of evaluate at the 3rd mark point to get a homology class in your, or equivariant homology class in your manifold, and then if you add in this loop parameter, then it turns out that's no longer, the quantum product is no longer the right or the natural structure to look at. Instead, you sort of are now looking at in the world of D modules. So you look at the quantum D module. So the equivariant quantum cohomology, in this case, it'll carry a certain quantum connection that differentiates. So in this, so you view it as a connection over a one-dimensional base, and you're differentiating in the direction of the Novikov parameter. Okay, so something that we proved is that there's a module action of this quantized Coulomb branch on the quantum cohomology of M. Well, you know, so just saying there's a module action, that doesn't tell you very much, but in particular, so if we, I'll explain how this, you know, the rough idea of this module action in a moment, but if you take the support of, so if you set your U variable, which I was thinking of this as the equivariant variable, equal to 0. So then you're just looking at a module over this commutative Coulomb branch algebra. And then you sort of also set the Novikov variable equal to 1. So the Novikov variable here, by the way, it anyways has degree 2. So you can think of it as setting q equals to 1, or just regarding if you have something which is linear over something with degree 2, it becomes 2 periodic. So you're just sort of focusing on the even and the odd part. Really, that's maybe a more precise way to say it. But you just take the even and the odd part, and then it becomes a coherent sheaf on this. Well, maybe I should say this BFM space, the spec of this algebra, and its support is actually Lagrangian, holomorphic Lagrangian. So yeah, I've messed up my notations here. Sorry about it, I apologize. But yeah, there's many different, as I said, there's many different names depending on whether you want to think of this as being attached to the group or to its Langlands dual. So I kind of messed this up, but in any event, you get a module over spec of the algebra where you set S1 parameter equal to 0, and it's a holomorphic or algebraic Lagrangian subvariety. And the idea of the proof, this is why it's important to sort of look at quantizations, is that if you have a module that extends to the quantization, then its support will automatically be coisotropic for the Poisson structure given by the induced by the deformation quantization. That's a result of Gauber. And in this case, as I said, that gives you this symplectic structure. But it's coisotropic, but if you kind of, in this particular case, it's you can easily see that it can only be at most half dimensional. So in particular, it's Lagrangian. So yeah, what is this module action? Oh yeah, maybe before I explain how the module action is constructed, I should tell you some examples of what happens in the simplest possible cases. So in the simplest possible cases, like would be a toric variety, a Fano toric variety, and then so any Fano toric variety, it has a fan associated to it. You can, so like for P2, I'll draw the fan. So for P2, it's something like this. And then, there's some primitive generators for the rays of the fan. And so the primitive generators here would be 1, 0, 0, 1, and -1, -1. And then basically these determine monomials on the dual torus. So, and what are those monomials? So in this case, it would just be like, if I have two variables, it would be Z1 plus Z2 plus 1 over Z1, Z2, something like this. And that gives me, in general, it's the exact same recipe, just the fans that get more complicated. Let's give me some function on the dual torus, which is called the Hori-Vafa superpotential. And then what I do is I just look at the graph of this of the derivative of this function. And that gives me this, and that's the Lagrangian. That's basically Giventhal's some version, some formulation of Giventhal's calculations. Mirror theorem. Okay. So basically the starting point for this construction of this module action is the following sort of construction of Seidel. So if you have a co-character, let's just for simplicity, we're going to look at the abelian case first. And it could be, you know, for what I'm about to say, you could imagine, in fact, any Hamiltonian loop, but once we get to equivariant structures, it'll only make sense in this more restrictive setting. So I'm thinking of this co-character as defining for me, you know, I have a manifold with a Hamiltonian T action, and it defines for me a loop inside of the Hamiltonian group. And so I can make a fiber bundle over CP1 with the following construction. So sorry, I guess I should really so this vector, I'm thinking of these are as coordinates on the boundary of my disk, and I'm going to glue two copies of a disk cross M. And so I'll glue their boundaries, but then I'll use the co-character to define the gluing in the fiber. And that gives me a fiber bundle over CP1. And you can do this in algebraic geometry. You know, the space can be made. If you started with something that's algebraic and you have a group action, then it would be an algebraic variety, or, you know, certainly in the symplectic world, it's a symplectic variety, it's a symplectic manifold. But the fibers at 0 infinity are canonically identified with M. And so I take this fiber bundle and I look at holomorphic sections. So I put some, you know, there's some symplectic structure on this. I look at holomorphic sections, which you know, at one marked point will go through the fiber at 0, and at the other marked point will go to the fiber at infinity. And there's sections in that, meaning that when they project down to CP1, it's an isomorphic. They project isomorphically down to CP1, and so using this moduli space, you got a push-pull operations. I'm thinking of Z as like a cycle. You could, you know, maybe it's a naive way to formulate it, but and I'm thinking in this monotone case, you can make this into a pseudo manifold. It's just maybe a technical remark. So it really will be like a geometric. You can think of this fiber product really as a geometric fiber product. In general, probably you have to do some kind of virtual fundamental classes, but never mind. And then you got some operation which is called the Seidel operator, from the quantum cohomology to the quantum cohomology. And and so the properties, so it has certain algebraic properties, and I put Seidel 0 here because we're going to make things suitably equivariant in a moment. But you know, it has some some properties that if you multiply, if you compose two of these operations, that's like comes from just adding the co-characters. And if you just look at a co-character and you send it to its Seidel of 1, then that's a ring homomorphism. So that gives just some element for every co-character, which I think of as a ring homomorphism from the the group, the grouping out of co-characters to quantum cohomology. And so that's great. So it's sort of a natural idea now to say, well, I have these T actions, let's try to do things respecting certain T actions. So what kind of actions can I put on this Seidel space? So of course I can act, if I look at the action by T on M, then I can kind of, that will kind of manifestly respect the gluing operation. So I get a T action on my total space. What's a bit more subtle is if I rotate over on this side, if I look at rotation in my base sphere and I try to lift that to an action of the total space, there's a certain asymmetry that you get, that you can lift it, but it's sort of a non-trivial action in that if the action of S1 cross T on so on one fiber, if you want that to be trivial, like the S1 cross T will act on the fiber at like at 0, it'll act just by S1 acts trivially and T acts by its action. Then at the fiber at infinity, it gets kind of twisted by what the action ends up being. So on the fiber at infinity, the action would be like S1 cross T acts by first applying the co-character to this S1 factor and using that to act on M. So there's sort of a something you can just check by hand when you try to lift the actions on the two copies of M are no longer symmetric, and that's why the Seidel operator fundamentally becomes sort of give you an action of a non-commutative, a quantized non-commutative ring, and yeah, so it in particular gives you an action of, instead of here, this is like the dual, basically spec of this is the dual torus. I can add in equivariant variables that would give me an action of the algebra underlying the cotangent bundle of the dual torus. But when I add in this additional loop symmetry, that gives me a non-trivial, the algebra that acts is this Coulomb branch algebra. So the Seidel operators induce an action of the abelian Coulomb branches on the quantum cohomology. And then if you want to do non-abelian groups, well, it's not so that much more complicated, really. What you do is, instead of instead of having a single loop, you have maybe a family of loops parameterized by some cycle. So your loop group now has positive dimensional cycles, but I can still imagine, I have some cycle B that parameterizes these loops, and over every fiber I build one of these Seidel spaces. So I can still do kind of a parameterized version where I count holomorphic curves parameterized by a cycle, and that's the generalization to the if I do this in families, basically that's what gives me these non-abelian Seidel actions, these non-abelian actions. So this is sort of the Lagrangian, the construction of the Lagrangian in the Coulomb branch. That's how it works. So So the question is, why is this of any interest? So let me make a definition. So what I'd like to do is kind of apply some semi-classical analysis now. So I say like, I have this, my BFM space or my Coulomb branch space. I have some Lagrangian in there, for any compact symplectic manifold or something along those lines. Maybe proper action. Proper moment map, sorry. And I want to know, like, you know, maybe there's some other Lagrangians in here. So as I said, there's this Toda projection to spec of H star BG. And in here you have, there's, you know, because it's a group scheme in particular, this a Hopf, this, you know, loop homology with a Hopf algebra, so it's a group scheme, and there's a unit section that's a group scheme. And you know, what is the meaning maybe of intersecting these two? So what is the meaning of intersecting? You can imagine that as, you know, again, some decategorification of taking Hom in this Rosansky-Witten 2 category that one wants to define. You know, and you know, I should say that we're not literally going to intersect the Lagrangians themselves. You know, of course, this Lagrangian here actually carries the quantum cohomology over it as a module. So really, you know, it's maybe a bit misleading to say we're going to intersect Lagrangians, but nevertheless, you know, you'll get something supported at that intersection. So let's say, so again, the simplest possible case is to put some kind of convergence condition on your manifold. So I'll call a moment map balanced if so, as you know, going back to a T-bot, the moment map determines a equivariant lift of the symplectic form, and there's, because my G-ax on the tangent bundle, I have an equivariant first turn class, so the moment map will be balanced if I have for my monotone symplectic manifold, if you know, if the first Chern class, equivariant first Chern class is equals the equivariant symplectic class, and I'll assume as before that G acts freely on mu inverse of 0. So in this case, your quotient is again a monotone symplectic manifold, and you know what we want to do is compute the quantum cohomology of that quotient in terms of the equivariant quantum cohomology. So here's the conjecture, which Constantine sort of a decategorification of what's in his ICM. So if I take the quantum cohomology, the equivariant, I look at it as a module over this algebra, and I tensor it with this structure sheaf of the unit section, and then I get the quantum cohomology of the quotient. So you can think of that as a, you know, he says for some reason it's quantization, I don't know. But it's you know, we'll try to explain where it comes from, how I think of it. So So if you trivialize your torus, we go back to the abelian case, then you get a very explicit formula, which just says that you just set your Seidel parameters, your Seidel operators that we constructed, all these operations, you set them equal to 1, and that gives you the quantum cohomology of the quotient. So it's this is sort of where I was going before, that in the quantum, at least in this setting, in quantum cohomology, the this ends up basically being a kind of a complete intersection quotient, like the number of these. This is some finite dimensional algebra, and the number of these variables like sort of cuts down the dimension of this ring from R to 0. So it's kind of nicer in some sense than the classical picture. So where does this, maybe I'll skip if you're not so familiar with Batyrev mirror symmetry, this formula, basically the main case before our result, the main case where this was proved was in for Batyrev mirrors. So if you think of a monotone symplectic manifold, by Batyrev for compact toric Fano varieties, viewed as a quotient of a vector space. Maybe I'll, some classical formula, but I'll skip it. So kind of what needs to be proved? So I'll just survey the proof. I'll just maybe focus mostly on the abelian case. And there's sort of two parts to the proof. One is to kind of construct a ring homomorphism from here to here. And the other thing is to prove, that will be surjective, kind of the way that this ring homomorphism is constructed. It'll be some deformation of the classical Kirwan map. So it'll be surjective just because the classical Kirwan map is, we can, by the strengthening of Kirwan's result, this, I should say this works in the abelian case. This works with any for any coefficient ring, actually. And here there might be maybe finally many bad characteristics having to do with when this is not a smooth variety, a smooth algebra. But you want to construct your ring homomorphism, but you need to, the main thing to prove is that after quotienting by this ideal of given by the Seidel operators, that what you have has exactly the right, so it's surjective, and you want to prove that it is exactly the right rank. And so the main theorem in this abelian case is that if you have a balanced moment map, this maybe is this should be R to the R, and apologies. Then the equivariant quantum cohomology is actually free over all of these. So you have these Seidel operators, the equivariant variable, and the Novikov variable, and the rank is exactly the rank of the quotient. So and so while our results are sort of can be stated in terms of algebraic geometry, at least for algebraic targets, our proof, we don't know of an algebraic proof for this. Instead, our proof uses Hamiltonian Flirt homology, so. And it's kind of motivated by Kirwan's proof, so I'll say sort of maybe the main. Few words about the main idea of it, so. So in here we have some mu inverse of 0. And let's say you're looking at norm of mu squared. So in Flirt homology, like so Morse theory corresponds to taking a very small multiple of your function. So Kirwan's stratification we think of as coming from, in terms of Flirt homology, taking a very small multiple of the norm squared function. So our, what we do is we instead look at what happens as you take this coefficient k, and you look at, instead of looking at very small multiples, you look at very large multiples. And if you're just thinking of classical Morse theory, that just multiplying a function doesn't really do much. But in terms of Flirt homology, where so the point of looking at a very small multiple is that all of your, when you're doing Flirt homology, you're really looking at periodic orbits of your Hamiltonian vector field. And for small multiples, the only periodic orbits are just constant, and they correspond to like the critical points of the function. But for large multiples, you get non-trivial periodic orbits. And in fact, if you kind of analyze what's happening, you have a lot of non-trivial orbits that sort of concentrate. So as k gets large, and so and in fact, the orbits sort of wind around in the fibers with different speeds corresponding to basically different co-characters. And so basically, yeah, so the result is that you can really make sense of this limit as k goes to infinity, where everything is sort of sucked into mu inverse of 0, and all the cohomology gets concentrated as different co-characters, multiplying the, so you get a kind of a free module over the cohomology of the quotient. So I think that's maybe I'm out of time, so thank you for your attention, and yeah.
Question?
I have a naive question. So after we take the S1 equivariance, the quantum cohomology is no longer a ring, is it?
Right.
Okay.
But it still becomes a module. This statement makes sense.
Yeah.
Right. So I formulated everything. I mean, the result. Yeah, I mean, it's a slight strengthening that's not needed. So for the main application, we don't have the U variable, but you can, the proof. This statement here works just as well with the U variable. So it's just you know, for the purposes of our argument, you could just work with non-equivariant quantum cohomology, but.
Okay, so in this case, we have a finitely generated ring extension as a, which is finitely generated as a multiple.
Right. Yeah. Right, so it's fine, it's, yeah, so if you take any. Any lift of generators of the Kirwan map, then those will generate the equivariant quantum cohomology.
Thanks.
Any question from Zoom? So let's thank the speaker again.